Welcome back to The Explainer. Today, we're decoding the abstract math behind mechanical stresses so you can truly master real-world joint design. If you've ever looked at a massive machine, a bridge linkage, or a heavy-duty tractor, and wondered how it doesn't just rip itself apart under all that immense pressure, well, you are in exactly the right place. Here's our blueprint for today. We've got direct stresses and formulas, exploring shear and torsion, cotter and knuckle joints, understanding modes of failure, and finally, exam prep focusing on problem solving. All right, section 1, direct stresses and formulas. Let's dive right into this.
To really grasp this, we need to think about these invisible forces physically. Imagine stretching a heavy rubber band as far as you literally can. That internal resistance fighting back against your pull is tensile stress. Now picture crushing an empty soda can straight down. That resistance pushing back against your compression is compressive stress. It's essentially the material's internal defense mechanism against outside forces.
So let's actually quantify that defense mechanism. For tensile stress, which we represent with the symbol sigma T, or sometimes you'll see it as 6T in older texts, it simply equals the applied force, P, divided by the resisting cross-sectional area, A. If you're taking notes, definitely jot this down boldly. Stress equals force over area.
Now, what if we reverse the force? Well, the formula mechanics stay exactly the same for compressive stress. Sigma C equals P over A. The math doesn't change, just the physical reality of it. The force is pushing inward, trying to crush the material, instead of pulling outward to stretch it. Here's a quick comparison to really lock these fundamentals in. Tensile is a pulling force, usually given a positive sign convention in calculations. Compressive is a pushing force, usually given a negative sign convention. But both absolutely share that core P over A formula. Make sure you have this basic alphabet of stress fully memorized, because the rest of this explainer totally relies on it.
Moving on to section 2, exploring shear and torsion.
Now, this brilliantly shows how tangential forces actually act. Instead of stretching or crushing, these forces want to slice right through a component. Look at the difference here. On the top, you've got single shear, where the shear stress, Q, equals P over A. But below that, in double shear, that force gets distributed across two separate sliding planes that effectively halves the stress, so Q equals P over 2A. Using double shear is a massive structural advantage in engineering. Then there's torsional shear stress. The definition sounds a bit complex: two equal and opposite couples acting in a parallel plane. But physically, it's super intuitive. Just think about wringing out a wet towel. That exact rotational twist you're applying with your hands is creating torsional shear stress right along the length of that towel. Looking at a cross-section of a shaft under torsion, check out the stress distribution. The stress is literally dead zero, right at the center axis of the shaft, and it linearly increases until it hits its absolute maximum at the outer edge. Basically, the further out from the center the material is, the harder it has to work to resist that twisting force.
Okay, section 3, cotter and knuckle joints.
So, we've got two distinct joints to categorize here. First, a cotter joint. This connects two rods rigidly to transmit axial motion, meaning straight back and forth, with absolutely no rotation allowed. It uses a flat wedge, which is the cotter. A knuckle joint, on the other hand, takes heavy tensile loads, but is specifically designed to allow for guided rotation. Think of the linkages on a tractor pulling a heavy trailer. Let's walk through the real-world anatomy of that knuckle joint. You've got the fork end and you've got the eye end. Notice how the single eye slides perfectly inside that double-pronged fork. And then they're interlocked by dropping a vertical knuckle pin straight down through the center. I highly recommend you grab a screenshot of these parameters or write these exact variables down right now. These are the standard parameters you'll use. F is your load, D is the main rod diameter, D1 is the pin diameter, D is the eye's outer diameter, and A and B represent the thicknesses of your fork and eye. These variables, they are absolutely crucial. They're the key to calculating whether your joint will hold steady or break. Which brings us to section 4, understanding modes of failure. So here's a critical engineering question for you. When you pull a joint with, say, 10,000 pounds of force, and it finally gives way, where exactly is the weak link? Take a second, formulate a guess based on what we've covered so far. Well, if you guessed any of these on the list, you nailed it. In our sort of structural autopsy here, there are 3 primary suspects. tension failure, where the metal just physically pulls apart at its thinnest cross-section, shear failure, where the pin or rod is sliced clean through, and crushing failure, where localized compressive stress basically deforms and flattens the metal inside the joint. Now, what's really fascinating here is how these failure zones perfectly map out. Look closely at the shaded regions on the eye and the fork. The heavily dotted areas facing the pin, those are the specific physical zones actively fighting against crushing deformation, while the cross-hatched areas on the sides are the exact zones fighting to prevent being ripped right in half by tension. Notice how a cotter joint can fail. Remember double shear from earlier? Because the cotter wedge passes through both the strap and the rod, it creates two sliding planes. If that axial force is just too great, you're going to get shear failure straight across both of those planes simultaneously. To actually predict and prevent these failures, engineers rely on specific failure theories. It really comes down to material science. If you're using a brittle material like cast iron, you apply the maximum principal stress theory, also known as Rankine theory. But if you're working with ductile, yielding metals like mild steel, you switch to the maximum shear stress theory, associated with Tresca and Guest. Because when it comes to metal snapping, you definitely want to rely on the right guest.
All right, final stretch. Section 5, exam prep and problem solving.
Listen, if you only memorize one starting point for a joint design problem, it absolutely has to be this fundamental tension failure formula. The permissible force, F, equals the area of a circle, so pi times d squared over 4, multiplied by the allowable tensile stress, sigma t. This equation directly dictates the required diameter of your main solid rods.
And here it is, your ultimate step-by-step joint problem-solving algorithm. Step 1, scan your exam prompt to find the given load and all permissible stresses. Step 2, use that formula we just talked about to calculate your main rod diameter, d. Step 3, use standard empirical proportions, like the pin diameter, d1, often just equaling the rod diameter, d, to figure out the rest of the joint dimensions. And step 4, and this is vital, verify the joint safety. Plug those new dimensions back into your shear and crushing formulas to make sure they don't exceed the limits. Stick to this algorithm, and you're going to solve it every single time.
I want to leave you with this thought right from the source material. To design is to formulate a plan to satisfy a particular need and to create something with a physical reality. By mastering these formulas for tension, compression, and shear, you aren't just passing a test. You are quite literally gaining the tools to safely shape physical reality. How will you use these principles to build the future? Keep practicing those steps, and we'll see you in the next explainer.